So Joseph, you said I should record on the computer, not
Yes.
on the cloud. Okay, did you get any message?
Yeah, perfect.
So, well, let's get started then. So today we have Andreas Braun. Well, thanks for giving this talk here. And Andreas will be talking about adiabatic fibrations, string dualities, and exceptional autonomy. So, Andreas, stage is yours.
Thank you very much. So, first of all, thank you for inviting me to Virtual Paris. I bought some croissant in the supermarket just a few minutes ago that I will maybe have after my talk because I didn't have time to eat it before. And they're not so bad up here in the UK, I have to say. So what I want to do today in this talk is I want to review some work I have done in the last few years with various people. And some of this work, you can think about this work from many different perspectives if you want. And so for today, I thought I will sort of give an overview over this work by using one specific perspective. And that perspective will be the perspective of string dualities, and in particular of some of fibering string dualities adiabatically to make new instances of string dualities. And we'll do that for exceptional autonomy manifolds. So all of these are big words. So essentially in the first part of my talk, what I'm going to do is I'm going to review a little bit some basic stuff about string dualities that I think by now are mostly textbook material. Then I will explain a little bit, or at the same time, actually, I will give examples of how one can use fibrations to create new instances from known ones. And then finally, I will speak a little bit about what it means if I say exceptional autonomy and how one can use the previous logic to understand something about string dualities in the context of exceptional autonomy. And of course, I don't know what is the style for the Rencontres, but I mean, of course, I'm very happy if you interrupt me. Happily, I even have a blackboard on my back, so I can write something on it, and hopefully you can read it if you have questions. To say one more thing, this topic at the heart is, of course, fairly technical, and I tried as much as possible to not give technical details. They're, of course, there in the background, but I'm not going to mention them explicitly for the most part. So if you want to know, please ask me and I can explain them. Okay, so let me start with something that is super well known, which is something that is called as T-duality. Namely, so if you open some basic book on string theory, they will tell you that if you have, say, bosonic strings wrapped on a circle, then that's equivalent to bosonic strings on another circle that has a radius that is not r. So let r is the radius of the initial one, and then the second one has radius alpha prime over r. And these two things are supposed to be equivalent physically. One way to see that is something that's going on there. Of course, the whole story extends beyond that is to look just at the spectrum, at the mass spectrum of excitations. And if I forget about oscillator excitations, then there's essentially two terms, and you can see that they're precisely being swapped. So this exists for any n and m, and the first two terms are swapped when I change r to alpha prime over r. Just to say alpha prime is a constant that somehow sets the tension of the string. And below I draw a little picture for you what these things mean. So the n equals m equals 0 sector just has to do with strings that somehow sit somewhere on this. So I imagine that there's not just a circle, but there's also some flat direction. So you can think about the whole of space-time as sort of a cylinder. And the n equals m equals 0 sector is just strings sitting somewhere. N equals 1, m equals 0. These are sort of KK modes of the higher dimensional excitation. So you can think about them as strings that are flying around, whizzing around the circle direction. And of course, as usual in quantum mechanics, that's quantized, hence n is an integer. And finally, and that's really the stringy bit, and that's what makes this whole thing work, what makes strings so special is that strings can wind around this as one. And for example, a state where, or a sector where n is 0 and m is 1 would correspond to a string that winds once around this S1. And of course, because strings have attention, the mass of that state will be proportional to the length of that string. By the way, I just realized it's unfortunate that I have an integer m and a mass squared m. Maybe you should imagine that this thing here, the m squared on the left-hand side, is a capital M, but I hope that's clear to everybody. Okay, let me now speak about something that is seemingly unrelated, and that's, let me first come from bosonic strings to superstrings. So if you look in your string theory textbook, there will be two superstring theories in 10D that are called type 2A and type 2B. And then if you look a little bit more, you will see that these have D branes, DP branes, where P is even for type 2A and P is odd for type 2B. And of course, they also have the corresponding higher form fields that couple to those branes. And now you can again ask, what is the action of T-duality in that setup? And what you learn is that T-duality doesn't just act on somehow elementary string states, such as here, but it also acts on the branes. So if you have an S1 and you have a DP brane wrapped on that S1 and you apply T-duality, then somehow it unwinds and it just has a position now along the S1 and it loses one direction. Now, of course, you can ask what fixes the position. Turns out that is the Wilson line that you might have on the S1 on the left-hand side. And vice versa, if you have a brane that is not wrapping an S1 and you apply T-duality, then after that, it wraps the S1. All right. So now I come to something that is seemingly unrelated, which is another classic story, which is called mirror symmetry. So mirror symmetry, to just say the slogan in one sentence, is the statement that if you have this type 2A string theory and you compactify that on, for the sake of being specific, a Calabi-Yau threefold X, then that is supposed to be physically indistinguishable from type 2B on another Calabi-Yau threefold that I just call XV here. So this statement that the physics is equivalent, of course, you can discuss that at many different levels. You can just, for example, you can just focus on specific aspects of these string theories propagating on X and on XV. And that's also how people came up with this. So one of the kind of most basic observations you can make is that if you take type 2 string theory on a Calabi-Yau threefold, you end up with the 4D n = 2 supergravity theory. And you can just look at the moduli spaces and you count how many vector and hypermultiplets you have in this 4D n = 2 supergravity. And turns out that in type 2A, you have H11 vector multiplets, whereas in type 2B, you have H21 vector multiplets. So if the statement that I gave above is correct, if these two physical theories are the same, then of course also the resulting 4D n = 2 supergravity theories have the same. So what I get is that H11 of one of these Calabi-Yaus must be the same as H21 of the other one, and vice versa. And some sense people would arrange these numbers in sort of little squares that they call Hodge diamonds, and then I think that's one of the reasons why they call it mirror symmetry, because you essentially mirror that array of numbers. And just as a comment, of course, these moduli spaces of string theory has something to do with geometric deformations of these geometries. Namely, H11 are what I call correspond to the elements, or the elements in H11 correspond to what are called Kähler deformations, and the elements in H21 correspond to what are called complex structure deformations of these Calabi-Yau manifolds. Okay, so as I said, this is just a very coarse way of looking at this. Next thing you might say is, look, string theory, fine, you speak about effective supergravity after compactification, but the real deal of string theory is, of course, that it's a two-dimensional superconformal field theory living on a world sheet. And how about that? And again, you can discuss the story from that point of view. again, there's many different versions of how you can phrase that. But one thing that is particularly fascinating, and I think that was one of the first really strong indications that this story is one that is true, is what I called Gettner models. So if you have superconformal field theory, so in this case, it's 2,2 superconformal field theory, you can ask about the representation theory of that, and then you can come up with what I call minimal models. So these are like simple, in some sense, irreducible representations of this superconformal field theory. And then Braun and Gettner pointed out that at a specific point in the moduli space of these Calabi-Yau manifolds, you know the worldsheet CFT exactly in terms of these minimal models. And the nice thing now is that using that idea, you can both give a construction of such a pair, and you can then, of course, and the construction is such that the resulting superconformal field theories are identical. Now, that's quite an impressive result, I think, especially for the time. As I explained on the last slide, or mentioned at least, these type 2 theories have all kinds of d-branes, and if you just look at the worldsheet superconformal field theory without any boundary operators, then there's no d-branes in the game yet. So of course, saying that the physics is equivalent also entails that sort of the spectra of d-branes of type 2a on X and type 2b on X V are equivalent, and that has led to all kinds of work in mathematics to trying to prove that, or trying to formulate what these things are, and that's something that goes under the name of homological mirror symmetry. And final thing I have to mention about this is not just a beautiful result about relating these two geometries and the physics on them, but you can also use that for mathematics. And especially there's a classic result from '91 by Philip Candelas and company that has led to lots of interest in mathematics, which is that what might be quantum corrections on the type 2a side. So these are what I call worldsheet instantons, where what you have to do to compute them is somebody gives you a homology class on X, and then you have to count in how many ways can I holomorphically embed a curve into X such that the image is in that homology class, and I have to count in how many inequivalent ways that is possible. Now, I said this in a very rough way, and if you want to define this properly in mathematics, that's already a subtle thing. But the cool thing is that once you have this mirror symmetry and you understand how to map things across, then what you will learn is that the same quantity that gets these corrections in type 2a, which is just like a prepotential, if you want, in the n equals 2 theory, that is something you can work out at tree level on the type 2b side. And that's, of course, a very fascinating thing. So that means you essentially what you have to do on the type 2b side is you have to work out some transcendental integrals, and then you have some expansion, and then the coefficients of that expansion predict for you in how many ways you can embed these spheres. These things have a nice name. They're called Gromov-Witten invariants, and computing them and checking with previous results in mathematics was a major success. All right, so now let me come back to the thing I started from, and that is the following realization that I can phrase as a slogan, and that's the name also of the paper where this was first proposed, which is mirror symmetry is T-duality. So let me maybe explain in a few minutes how people came up with that. So if you have strings propagating on some Calabi-Yau manifolds, there's supersymmetry, and in particular, there are BPS states. And you can ask about which BPS states do we have on both sides. And on the type 2a side, there will always be BPS state that has to do with a D0 brane. And the D0 brane is a one-dimensional object, and you can think about, but it has only somehow it's only a point in the space-like direction. So you can think about this as just a point that is flying around on this Calabi-Yau manifold X. So that means the real moduli of this thing are just 6. It's a Calabi-Yau threefold, so complex 3, real 6-dimensional. So it has 6 degrees of freedom, this thing. And now I can also ask about this is not the only one, but this PPS state will always be there. On the type 2b side, I have the odd branes. So meaning D-1, D1, D3, D5. So now a D3 and a D5 brane, I cannot put that on a Calabi-Yau manifold such that I get a BPS state. That has to do with the fact that there are no cycles. There are no 1 cycles or 5 cycles I could wrap such a thing on. So the only candidates are D3 branes. And it turns out that there are special submanifolds of such Calabi-Yau threefolds that are called special Lagrangian threefolds. So call them L. You can think about that intuitively as if you look at local coordinates, they will be purely along holomorphic or purely along anti-holomorphic directions of that Calabi-Yau manifold. And if you wrap a D3 brane on that, you also get the BPS state. So if this mirror map makes any sense, then of course the BPS states on both sides should agree, and we can try to map them across. And that in particular means that this special one, this D0 brane on X, has to be mapped to some D3 brane on XV that is wrapped on some L. And we already counted that we have 6 real degrees of freedom, and so we can try to compare that with the degrees of freedom of such a D3 brane wrapped on L. Now, it turns out that the moduli of such a BPS D3 brane are given by 2 times the first Betti number of this special Lagrangian 3-cycle L. And where that comes from is that you get B1 of L Wilson lines that you can have on the D3 brane. I mean, that should be pretty obvious. But furthermore, B1 of L also counts the deformations of this D3 brane. So you can move it around a little bit inside of the Calabi-Yau threefold. So because 2B1 of L is 6, that means B1 of L must be 3. So that means we have 3 deformations and 3 Wilson lines. So if we have 3 deformations and we're talking about a 3-cycle in a 6-dimensional space, that means somehow we can move it in all 3 of the transverse directions. And that means we can think about this XV as being actually fibered by L. So we can think about these 3 degrees of freedom as coordinates on the base of some fibration. Furthermore, if somebody tells you that you have a 3-manifold and the first Betti number is 3, of course, that doesn't imply that it is a 3 torus, but it is somewhat suggestive, or you might say the simplest choice, the simplest option that you could think of would be to take a T3. And now the realization of Strominger, Yau, and Saslov was to say, hey, let's roll with this a little bit. Let's just assume that that's true, that we take this as indication that we can think of the Calabi-Yau manifold to be fibered by 3 tori. And then we can think about this mirror map as nothing but T-dualities on the fiber. And because the fiber is a T3, we have to do 3 T-dualities. So we go from, say, type 2A to type 2B, back to type 2A, and then again to type 2B. And the reason you cannot simply do 1 T-duality or 2 is because globally this fibration is non-trivial and different directions of this 3 torus are swapped with each other. So the picture that we could have is something like this. So this whole thing here on the left-hand side is supposed to be the Calabi-Yau threefold X. And by writing this arrow here, what I mean is that this whole space looks like whatever I drew here fibered over what I drew down here. So if you want to draw a 3 torus, I think a good way to draw a 3 torus is to draw sort of a box where opposite sides are identified. Well, that is in fact a 3 torus. And that will now be fibered over some 3-dimensional base. But if this was a fibration in the sense of fiber bundles, then the whole thing would be pretty trivial. What you need to get something non-trivial is that this fiber can degenerate somewhere. So over some loci of this 3-manifold, some of the 1 cycles of this 3 torus will pinch, they will collapse. And that also implies that when you move around such loci, so that such loci have to be at real codimension 2. So that means there's a notion of going around them and circling them. And if you encircle them, then there's going to be some monodromy, some non-trivial map acting on this 3 torus. And turns out that this loci where you can have this monodromy, the loci where this 3 torus degenerates, have to be, or at least in first approximation, if I'm careful, is sort of a trivalent graph. So it's a graph, and sometimes things can come together, and they're always such that 3 things come together. Now, on the other, there's this little window here that I have to move out of the way. So now the idea is that if you give me one Calabi-Yau threefold X, and I can work out what this vibration looks like, I can get the mirror Calabi-Yau just by replacing this torus by the mirror space, so by the one where the radii are inverted, and then I get the mirror manifold. But crucially, we're doing this translation fiber-wise, so the base and the degeneration loci stay the same in both cases. And so first of all, there's a bunch of standard constructions for Calabi-Yau threefolds, and for most of them, it's actually possible to work out what this looks like. It's not completely straightforward. You have to go into a specific limit, which is called the large complex structure limit. But in that limit, you can actually work out what this looks like, and you can verify that this idea of Strominger-Yau and Suslov is not completely crazy. However, one thing that you have to keep in mind, and that will stay important as we go along, I will not mention it explicitly most of the time, but the idea, of course, here is that we understand that 2 things are the same. For example, type 2a and type 2b on a 3 torus and the dual 3 torus. Then, of course, if that 3 torus changes over some base manifold, and it changes very slowly, then it's, of course, reasonable to suspect that that means that I can still relate the 2 situations in a one-to-one fashion, if nothing too crazy happens. And that's something that people typically call adiabatic fibrations. If I want to phrase this more mathematically or more precisely, I would say the fiber changing slowly over the base can be arranged by making the base very big compared to the fiber. So in some sense, this is the limit we will always be in here.
Andreas, can I ask a question? Sorry, I'm supposed to raise my hand. I'm not sure this. Can I just ask a question, Andreas? Hi. You just said that for most constructions of Calabi-Yau, so we're talking compact and the large, okay, so with the B-model large complex structure limit, you can explicitly give this loci on the base.
Yeah.
So if I give you the quint, yeah. If I give you the quintic, you can.
Yeah, for the quintic, you can do it. I mean, there's actually, I can recommend you, there's a very nice review by Dave Morrison about this, and there will be pictures of that. So I can explain to you in a few seconds how this works if you want.
I'd be happy to hear it, yeah.
So what I have in mind, of course, is like if you want the most like general construction of Calabi-Yau threefolds and their mirrors is given by what I call reflexive polyhedra. That's the Batirov construction. So there, the input data is a 4-dimensional polyhedron that has the special property that's called reflexive, but doesn't matter what that is for us now. So
but you're talking about hypersurfaces. It's not the most general.
Yeah, hypersurfaces of those. I mean, the polyhedra correspond to toric varieties and at the same time define for you hypersurfaces, right? And so think about a 4-dimensional polyhedron. Now it has a bunch of faces and all of that. So the polyhedron, you can, I mean, it's a 4-dimensional polyhedron, and you can think about that. You can think about the kind of the surface of the polyhedron as giving you sort of a triangulation of a 3-sphere. Yeah, because the surface of the polyhedron is some 3-dimensional object, and because it's convex and all of that, it essentially topologically is a 3-sphere. Yeah, and you should identify that 3-sphere with the base of this vibration. So instead of M3, I should have just written S3. Simplest possible thing you could think of. It's just a 3-sphere. Yeah, and then what you can do is that to actually define the Calabi-Yau properly, you have to there's a notion of integer stuff, integer points on these polyhedra, and you have to triangulate all of the faces of this polyhedron. And then from this triangulation, you can actually construct this trivalent graph. That's how this works. And the reason somehow the reason that the graph sort of is effectively two-dimensional has to do with the fact that this four-dimensional polyhedron has faces of dimension 3, 2, 1, and 0, which are the vertices. But it turns out in this construction that the faces of dimension 3 are completely irrelevant. All that matters is faces of dimension 2, 1, and 0. So you only look at the triangulation on the 2D faces, and that is something that looks effectively two-dimensional, like this tribundant graph. And the different faces then touch somehow, and then these things are stuck together.
Okay,
So that's how this goes. And the quintic and its mirror are just one example like that. I will make another example that works completely differently in a little bit.
Andreas?
Yeah.
Another question here. So you're talking about this adiabatic limit where the fiber is way smaller in one of the manifolds, but if you keep this notion of T-duality as inverting the size of the circle, so shouldn't you expect the opposite behavior in the mirror manifold? Or?
Well, the point is that there's an alpha prime in there. So it's not really inverse. It's like inverted with respect to the alpha prime.
Okay.
So in principle, you can still have that. But yeah, cheers. That's a good point.
Okay.
So it's kind of subtle. I mean, it's also kind of subtle because now I told you that X and XV are topologically different manifolds. And from this picture, you might think, hey, well, if all I'm doing is the torus is like a different torus, why are they not topologically the same? They are, in some sense, they have the same Euler characteristic, for example, but otherwise they're not quite the same. So there's lots of devil. The devil is in the details here. So I'm sorry if I brush over that. But I mean, for this picture, I mean, there's lots of good papers by Mark Gross about this, who worked on this extensively. And there's a nice review by Dave Morrison I can recommend. Okay. Where also this is extended to complete intersections and blah, blah, blah. So this is all something that people have looked at. All right. So now let me speak about a different classic topic. That is the relationship between type 2A string and what people call M theory. So the idea is as follows. So maybe I should have given some references here. I omitted that, but I guess most people know these papers. So there's a bunch of famous papers about this by Witten and also I think Hull and Townsend from the mid-90s. So the idea is as follows. There's type 2A string theory, and it has a string coupling, and you can ask what happens to that string theory when the string coupling gets strong. So we can't do the usual string perturbation theory anymore. And the first instance or the first situation in which you might ask this question is you might just say, let me not talk about the full type 2A string theory. Let me just look at the 10D supergravity I get from that. And then if you do that, it's not difficult to see that if you take 11-dimensional supergravity and you compactify it on a circle, then you get the 10-dimensional type 2A supergravity. Now, the 11D supergravity is unique, but in 10 dimensions, there are several maximal supergravities. And if you put the 11D supergravity on a circle, you get the type 2A one. And people knew already that which parameter in this supergravity action you should relate to the string coupling, and that tells you that the type 2A string coupling you should think about as being related to the radius of that compactification. So first of all, that's cool because if the radius is big, so that the string coupling is big, then the 10D perturbative string theory isn't really useful. And this picture tells us, yeah, it's obvious. Radius is big, so you're supposed to describe this whole story in the 11D terms. On the other hand, if the radius is small, string coupling is small, we know perturbative 10D string theory is a good thing to do. And that also means that it's good to study the 11D theory in terms of the KK theory. So in terms of 10 dimensions. So people came up with this idea that there is some 11-dimensional theory that they dubbed M theory that describes the strong coupling limit of type 2A string theory. And the low energy limit of that should be given by 11-dimensional supergravity. And the circle is then typically called the M theory circle by most people. So that's the basic idea leading to M theory. And again, there are fibered versions of this where you say, hey, what if I have this 11-dimensional theory? So let me just go to low energy and speak about 11-dimensional supergravity for the time being. And I consider a situation where this 11-dimensional theory is compactified on something more complicated that has a circle fibration. And I think the most famous notion of that, or the most famous instance of that, is if you look at M theory on what is called a Taub-Knot metric, or a space with a Taub-Knot metric. So that's a real 4-dimensional space. So here in this picture, this 4-dimensional space would be along the directions x7, x9, x7, x8, x9, and x10. Well, that takes you from 11 dimensions to 7. And it turns out that this Taub-Knot metric is such that it's the circle fibration over R3, where the circle degenerates over a bunch of points. And if you change the metric, you can move around these points where the circle collapses. Now, if you match that with the type 2A story, what you're going to realize is that that describes for you a type 2A setup where you have a bunch of D6 branes in flat space. That's one of the things that are quite pretty, and you can check lots of stuff, and you can work out the spectra on both sides, and it works very well. One thing that is quite cool here is that if you have 2 D6 branes and you put them on top of each other, then you know that you're going to have some gauge enhancement to some non-abelian gauge group, say SU2 or in the flat space U2. And now you can ask, where do those degrees of freedom come from? And if you look at the geometry of this circle fibration, you're going to see that there's a 2-sphere between, if you take 2 of these points, so this is supposed to sort of be lift of this picture into the 10th direction, then between, I mean, you take a path that connects these 2 points, and everywhere on this path, this M-theory circle will have a finite size, but it turns out that over these points, the M-theory circle will collapse, so you get sort of a sausage-shaped 2-sphere. And when I put the 2D branes on top of each other, this 2-sphere collapses, and it turns out that that corresponds to a singularity for this Taub-Knot space. Now, at that point, this 11-dimensional supergravity is not useful anymore. And to make sense of this M theory, I have to speak a little bit more. And the usual kind of folklore statement that you can, of course, substantiate with lots of examples is that there are further objects in this M theory, namely there are M2 branes. If I wrap them on this thing, they correspond to BPS states. These BPS states have the right quantum numbers to give me the W bosons that enhance me from U1 times U1 to U2. And it's quite pretty to work out how that works, and it does. So somehow the idea is that M theory is low energy is described by 11-do supergravity, which is fine on smooth geometries. When geometries get singular, I have to carefully see how they become singular, and I can figure out the extra states I get from some wrapped membranes. Okay. There's a cousin of this idea that people typically call F theory, and because I will not speak a bunch about F theory in this talk, but I've worked on this a lot in my career, so maybe let me say that in a few words. So we just said M theory on a circle is the same as type 2A, so I can put M theory on a product of 2 circles. And that gives me a 2 torus that I can also realize as an elliptic curve, so I can write that, call that E. And now that's supposed to be the same as type 2A on one of those 2 circles, but now we can do T-duality, and I can T-dualize to type 2B on a circle that has a different radius from the first one. So if you go all the way from the left-hand side to the right-hand side and you compare stuff, what you're going to find is that the volume of this product of circles of this elliptic curve on the M theory side is the same as the inverse, or related to the inverse of the circle on the type 2B side. Furthermore, I can describe the metric here as describe E as a complex manifold if I want. And then one input for the metric is the tau parameter of that elliptic curve. And it turns out that's related to the inverse of the string coupling and the C0 form on the type 2B side. Now, just as a comment, people had already figured out a long time ago, I think that was Peter West and company in the 80s, that in type 2B, there is an SL2R self-duality that works like electromagnetic duality. And the quantum version with D branes and all of that, that should become SL2Z. And now this relation, and it acts on C0 plus IGS to the -1 in the way you would expect it to act on a tau of an elliptic curve. And now sort of this gives you a geometric explanation for why that has to be the case. Okay, The idea of M theory is very simple now. It's just fiber this data on both sides. So on the M theory side, fiber this elliptic curve over some base manifold that you want to choose to be a complex manifold, because there's some equations of motion tell you that you want to have something holomorphic that gives you a total space that has to be Calabi-Yau, again, by the equations of motion. And on the type 2B side, what we have is just this complex manifold B times the S1, this one up here. And this tau field, of course, now varies along B in a way determined by the way E varies over this base B on the M series side. And this is not typically what people call F theory. What people call F theory really is the limit where I now use this relation to decompactify this S1. So I shrink the volume of E here, and I decompactify the S1 here. Now you might, to make one more comment, now you might say, what the hell does that mean to have type 2B on some complex manifold? Don't we need the Ricci flat metric or something like that? And the answer is, that's right. But now that would be the case if tau is constant. So, but now here tau varies. And tau is, of course, coupled to D7 branes and oriented fold 7 planes. So you should think about B and the tau variation as being a way to describe a type 2B oriented fold with O7 planes and D7 branes, or a non-perturbative version of that, which is what people typically call F theory. All right. So finally, let me say a few words about heterotic things. Things get a little bit more complicated now. So I haven't spoken about heterotic things at all now, heterotic strings at all so far, but I'm assuming that you have at least some familiarity with them. So we can look at heterotic strings compactified on a 2 torus or a 3 torus or a 4 torus. And these are classic things that people have studied. And if you do that, the moduli space of those effective theories is an Orion moduli space, which are just Grassmannians. Now, for a 2 torus, you get Grassmannian of 2 planes in a 18-dimensional space. For T3, you get the Grassmannian of 3 planes in a 19-dimensional space. And for sorry, it's a 2-plane in a 20-dimensional space of signature 2,18. So this is what this notation means. Sorry about that. For T3, you get a Grassmannian of 3 planes in a 22-dimensional space. And for T4 planes, you get the Grassmannian of 4 planes in a 24-dimensional space. Now, okay, fine. This is like a very classic results on toroidal compactifications of heterotic strings. Now, the funny thing is we can look at some of the stuff we've spoken about already, F theory, M theory, and type 2A. And then you realize if I take a K3 surface, so a K3 surface is the unique complex two-dimensional Calabi-Yau manifold, and I put F theory on such a K3 surface, or M theory, or type 2A, I recover precisely the same moduli spaces, which is very beautiful and very special, and leads you to suspect that there's a duality between these things. And again, that's something that people have considered already in the 90s and where multiple checks have been performed. If you want to learn more about this, by the way, there's some very nice notes by Paul Aspinwall about this that I can really recommend.
Actually, Andreas, you're missing a dilaton factor in the moduli space.
That is true. I apologize. Yes, of course. So there is always a dilaton factor, and that corresponds to the total volume of this K3 surface, if you want. Thank you very much, Boris. That's right. Okay, so the moduli spaces that so these Grassmannians also have a very basic or very simple interpretation. Up to some details that I'm glossing over, you can think about them as follows. So this K3 surfaces have a middle cohomology, H2 of these K3 surfaces. And the kind of part of the geometric data that is relevant to F theory, you can think about as taking the holomorphic 2 form of this K3 surface. So this is a holomorphic harmonic 2 form inside of this second cohomology group. Now, you can just think about it as a 2-plane in a vector space, modulo some constraints that then end up telling you that up to the overall volume, so up to the dilaton, the moduli space is going to be that one. Similarly, in M theory, actually in M theory, the situation is a lot simpler. There you have to give me the moduli space on the M theory side is just the Ricci-flat metric on the K3 surface. And it turns out that's given by a 3-plane in a 22-dimensional space. 22-dimensional space is just really bona fide this middle cohomology. And the 3-plane, the lags of the 3-plane, you can think about the real and imaginary part of the holomorphic 2 form and the Kähler form. And finally, in type 2a, it's again the same data as an M theory, but now we have a string theory and there's a B field. And that gives you sort of the 4th lag of this Grassmannian. And in particular, this type 2a story is something people have studied already very early in a fibered version. So there's a very nice paper by Kashu and Waffa from '96 where they, I think, proposed this for the first time, which is to say, hey, let's look at this duality here, the one between heterotic strings on T4 and type 2a on a K3 surface, and let's just fiber that. And we do that in the same way as before. We just fiber the same data over a common base. So on the type 2a side, I'm going to have a K3 surface S that's fibered over a CP1. And if I want to get a 4D theory with some supersymmetry, so e.g. 4D n equals 2, then we should arrange for this fibration to be such that we get a Calabi-Yau threefold. And it is not difficult to write down Calabi-Yau threefolds that have such a structure. And already in the 90s, people had long lists of examples of such spaces. And I think that was one of the reasons why people found some evidence that this idea that I'm explaining is correct. So it's not difficult to make these kind of examples. And now on the heterotic side, we have to fiber. Now we have to replace this K3 surface with a 4 torus that is now fibered over CP1. And furthermore, of course, on the heterotic side, the data isn't just about the geometry, but there's also a flat connection on this torus. And of course, I have to fiber that as well in an appropriate way. And it turns out on the heterotic side, of course, if we want to have 4D n equals 2, we can't just have it on a Calabi-Yau threefold. One thing that you might immediately come up with is another K3 surface that I might call S hat times a 2 torus and some appropriate, how did that happen? And some appropriate, what happened now? Ah, yeah, here we are. So, and some appropriate, sorry, I touched the wrong button. So, and some appropriate bundle on this geometry. Now, I said before, you should think about some of the 4 lags of this torus that have to do with this Grassmannian as being related to the holomorphic 2 form, Kähler form, and B field on the type 2a side. Now, if you construct one of those geometries, a Calabi-Yau threefold that is a K3 surface fibered over CP1, then actually the Kähler form and the B field are constant over this base. They don't do anything. The only thing that varies non-trivially is the complex structure given by the holomorphic 2 form of this K3 surface S. So that means here only 2 lags of the T4 are fibered non-trivially over CP1. That's why you get this T2 factor. That's all very nice and that all works very well. And people have studied lots of instances of this duality. And let me stress again, of course, it's something I can think about purely from the 4D n equals 2 point of view if I want, but it's also something that I can at least motivate strongly by fibering a known higher dimensional duality. And just to say, maybe I want to say one more thing about this, which is that this is also something that you can use to make cool checks between the two n equals 2 theories that you get on both sides. Namely, on this side, on the heterotic side, for example, there's going to be some gauge theory in the 4D n equals 2 theory. There's going to be some gauge kinetic functions. They receive some threshold corrections. And it turns out that these things you can recover from the Gromov-Witten invariants on the type 2a side, which were these sphere or holomorphic curve embeddings that we can compute using mirror symmetry. So that's cool how all of these things tie together. Okay, so after this like review about a few string dualities and how you can fiber them or what they have to do with fibrations, let me somehow zoom out a little bit. So far, all of the geometric stuff we have done had to do with K3 surfaces and elliptic curves and Calabi-Yau manifolds. And the reason these things popped up was that famously by Yau's theorem, Calabi-Yau manifolds have Ricci-flat metrics. And because they have Ricci-flat metrics, they are good backgrounds for string theory or for supergravity theory. And now, of course, you can ask what other instances of such geometries do exist. And there is actually no general theorem that says every Ricci-flat geometry has to do with what is called a special holonomy manifold. But the converse is true. So if you give me the manifold that has the right holonomy group, then one can prove that there exists a Ricci-flat metric on that manifold. And just as a reminder, so holonomy group means you have a manifold, there is a metric, there is a connection, there is a notion of parallel transport. I can take a tangent vector, I can parallel transport it on a loop. It comes back to a different tangent vector. And if I consider all of the path on the manifold, then that gives me a group of maps, and that group is called the holonomy group. And for a Riemannian manifold of dimension n, it's typically SON, which is like the generic expectation you might have. And so clearly it's something special if it's less than SON for an n-dimensional manifold. And a mathematician named Berger at some point in the last century compiled a list of what options we have. And the options I show here, some excerpt from this list, are just the ones where the reduction holonomy actually implies the existence of a Ricci-flat metric. And what is really curious there is, of course, Calabi-Yaus appear. They exist in any even dimension, and they have two covariantly constant spinors. That was the reason, for example, we ended up with n equals 2 supersymmetry in 4D if we put type 2 strings on a Calabi-Yau threefold. Then there's the symplectic ones, so they're called hyperkähler manifolds. They preserve even more spinors. But there is two really odd ones that don't exist in any even or any dimension that is a multiple of 4. They only exist once in dimension 7 and 8. It's really special. Oh, it's some like the exceptional groups or the exceptional Lie algebras or sporadic groups. Now these things exist only once. And they're called G2 and spin 7 manifolds because they have G2 and spin 7 holonomy, and they only exist in dimension 7 and 8. Furthermore, they only have one covariantly constant spinor. So they preserve minimal supersymmetry, if you like. And what's very curious is that if you look at M theory or 11D supergravity, we start from 11 dimensions. And I did a little computation for you here. So 11 minus 7 is 4. So that means G2 manifolds give you 40 compactifications of M theory with minimal supersymmetry. That's quite, I think that's quite intriguing, no? That there is this exceptional case that has to do with 4-dimensional M theory compactifications with minimal supersymmetry. And similarly, spin 7 manifolds would have to do with minimal, so n equals 1 theories in 3 dimensions that you get from M theory. Of course, for that reason, people were quite excited about these kind of things. And there was a lot of work on that roughly 20 years ago, a little bit less, but people didn't do that much. And the reason is that these things are difficult to construct. Yeah? So Calabi-Yaus are complex manifolds. We can realize them as algebraic varieties, and we can use complex algebraic geometry, and then we're very powerful. But that's not true for G2 or spin 7, unfortunately. So the classic examples of G2 manifolds were compact, were written down by, I mean, there's earlier non-compact examples, were written down by Dominic Joyce in the 90s. And you do something that is very natural for a string theorist. You take a 7 torus, you make an orbifold of that by a finite subgroup of G2, gamma, and then, of course, that part is easy. The hard part is to then show that there is a smooth manifold you get by deforming that. And that's the tough work that Joyce did on this. You can do the same trick for spin 7. You take T8 and gamma, a finite subgroup of spin 7, and then you can make compact spin 7 manifolds. And I will at least, let me make one comment about questions such as what does string theory to do with the real world? Of course, because 11 minus 7 is 4, you might say, okay, great. So if we want to learn something about 4n equals 1 theories, we should study M theory on G2 manifolds, which is precisely something that people did a lot. The problem is that theory you will get if you take a smooth G2 manifold will be rather boring. So these G2 manifolds have non-trivial Betti numbers B2 and B3, and you will just get B3 chiral multiplets and B2 U1 vectors. And these chirals are uncharged under the vectors. Well, that's very boring theory. And if you want to get some interesting gauge sectors, what you have to do is you have to have singularities on that G2 manifold. And there's a little dictionary between which codimension of singularity has to do with which kind of gauge theory data. And people have made non-compact examples of these situations. In particular, the point-like singularities have to do with chiral matter. So that's really the interesting thing. And there's a very nice paper by Witten and Bobby Acharya where they wrote down examples, non-compact examples of that. But to date, nobody has constructed a compact G2 manifold with point-like singularities. Nobody has done that. And it's difficult. And of course, the kind of, for the Calabi-Yau manifolds also, there's similar situations where you want to engineer singularities to engineer some interesting gauge theory or some superconformal field theory or whatever. But there, you can be very, you can define these things as algebraic varieties, and you can very explicitly see how you can tune the defining equations to give you some singularity. And that technique you don't have for G2. You have much less at your disposal. And the techniques that people typically use to construct these things are more differential geometry techniques. And then you get, somehow speaking about singularities is something that becomes a little bit harder. And typically mathematicians also are very shy to talk about that, which is a problem. It is certainly a problem. So, oops, what happened now? Somehow a slide came here that wasn't supposed to be here. That's very interesting. But anyway, so no, sorry, that is actually the slide that has to, sorry, I confused myself. So what I want to talk about next, or for the remainder of my talk, is I want to talk about using similar logic to the logic we have had before about using string dualities in a fibered version to get lower dimensional dualities between string theories or M theory on different geometries to learn something about these exceptional geometries. Or rather, I want to explain how to come up with instances where these appear in some duality. And of course, one of the motivations for that is that, hey, if we feel like we have some Calabi-Yau stuff and we understand that well, but now we have a dual version where we have one of these exceptional holonomy manifolds, then maybe we can learn something about the exceptional holonomy manifolds from something that we know better. One motivation of doing such a thing. So here's a classic, very classic expectation that people have, many people have voiced already a long time ago, namely, I spoke a little bit about mirror symmetry and the fact that we should think about Calabi-Yau threefolds as being fibered by three tori over some base that we can think about as maybe a three sphere if you want. Now, as I explained a little bit before, heterotic strings on a three torus are equivalent to M theory on a K3 surface. So you might say, aha, so I can try to do that duality fiber-wise in such a situation. So I will have a three manifold and a three torus fibered over it, and now replace the three torus together with a flat connection by a K3 surface that is now still fibered over the same base and will degenerate over the same loci where this three torus degenerates. At least the first order, and roughly speaking. So now this thing here was a 3 plus 3 equals 6 real dimensional space, but the K3 surface is 4-dimensional. So now I get a 4 plus 3, which is a 7-dimensional space that I'm compactifying my M theory on. And the resulting theory I get, I can see from the left-hand side, should be 40n equals 1. So that means that this manifold that I have my M theory on should be a G2 manifold. So that's a very classic idea. You should think about G2 manifolds as being constructed by replacing the Somin-Jayaw-Saslov T3 fiber by a K3 surface in an appropriate way. So, and people had made examples of that in the orbifold context, where that way of thinking was justified. But beyond that, there are no examples of this, or there were no examples of this before we came up with some new ones. So let me explain that to you in a few seconds. So the trick is to look at a very specific instance of a Calabi-Yau threefold where we understand the Somin-Jayaw-Saslov vibration very, very well, and it's very simple. And that thing is called the Schön-Calabi-Yau threefold. So the Schön-Calabi-Yau threefold is a complete intersection in P2 times P2 times P1, given by two equations with these weights, 3, 0, 1, 0, 3, 1. And well, if you fix a point on this P1, then the first equation gives you an elliptic curve in that P2, and the second equation gives you an elliptic curve in that P2. So the whole thing looks like a product of elliptic curves fibered over CP1. And if you work a little bit harder, not too hard, you can see that each of these elliptic curves degenerates over 12 points on this base CP1. I just have to compute some discriminant and its degree. So this whole Schön-Calabi-Yau threefold looks like a product of elliptic curves fibered over P1. And now, to see, the first thing we want to do now is we want to see what is this SYZ vibration. The trick how to see that is to say, hey, let me take the 12 points on this base over which this elliptic curve degenerates to the left, and the ones where that generates to the right of this CP1. And if you write down these things explicitly, you can convince yourself that that's possible. And if you do that, then afterwards you might want to cut it in two halves. So now on the left half, only one, the point about this is that on the left half, only this thing will be non-trivially fibered. This is the product, vice versa. And if you want, you can work out what these things look like. That's essentially this elliptic curve times that stuff. And that stuff actually turns out is the same as a rational elliptic surface, dp9, where you have excised one fiber. Same here. Now, that doesn't quite tell you yet about the SYZ vibration, because you should think about the coordinates on these things as each of these tori has a holomorphic and an anti-holomorphic coordinate, same with the base. But the SYZ fiber, you should think about purely in the holomorphic or purely in the anti-holomorphic directions. Now, it turns out you can somehow argue, because this thing is essentially a hyperkähler manifold, you can argue that the picture that you're drawing by somehow redistributing things such that you see the vibration purely by holomorphic or anti-holomorphic stuff is essentially the same. And I tried to draw that here. So maybe if that looks a little bit overwhelming, first look at the left-hand side. So the left-hand side is the same thing that we had before. Elliptic curve fibered over a cigar, degenerating over 12 points times a torus. But now I split the torus into two circles. And if you follow up what happens to the coordinates, so I put all of the holomorphic ones in the base, anti-holomorphic ones in the fiber. Now you do the same with the right-hand side, but then there is some mismatch, or rather things are now glued slightly differently. So here, this of course is glued to that, this is glued to that, and this S1 is glued here. But after I distributed my holomorphic, anti-holomorphic stuff in that way, the gluing works in that way. So this product S1 here is swapped with the S1 in the cigar and vice versa. And this kind of non-trivially fiber 2 torus and this extra S1 are glued like that. So one S1 just goes back to itself, and these are swapped. And now this whole story, now the three S1s up here are a T3, that is the SYZ fiber. And the rest is the base. So first of all, you can look at the base, you see what it looks like, and you can argue that that's actually a 3-sphere. Which is cool. And then, of course, this thing degenerates over 12 points times an S1. So that gives me a discriminant locus, which is 12 copies of an S1. Same happens on the right-hand side. And if you think a little bit about how these things are glued, you will see that these S1s form this sort of hop link, like here. And that's something you can see from this picture, but it's also something that people had figured out independently using other methods. By the way, this is a trivalent graph, just it has no vertices. So kind of a special instance. Now, if we want to have the M-theory dual, this G2 manifold of that, what we have to do is we have to replace this 3 torus by a K3 surface. This was the idea that I explained here. And now, somehow, as I said before, you should think about these 3 legs of the 3 torus as being related to the holomorphic real and imaginary parts of the holomorphic 2 form of the K3 surface and the Kähler form. And if you follow through with that, what you're going to see is that after you've replaced this T3 fiber with a K3 surface, actually things become quite simple. On the left-hand side, I mean, the base just goes along for the right. On the left-hand side, you have a K3 surface that is fibered holomorphically over this cigar. And that whole thing turns out is actually a Calabi-Yau manifold that is of the type that people call asymptotically cylindrical. So if I go towards the middle region, it's just a cylinder times a product. Same for the right-hand side. And this kind of funny swapping of circles corresponds to a hyperkähler rotation for the K3 surface. And, well, that's something that you can somehow, more or less derive from this physics picture, but it's also something that mathematicians have independently constructed, and they call this a twisted connected sum, G2 manifold. So if the pictures were a little bit much, here's a kind of more sober summary of the situation. So if I look at heterotic string theory on this Schön Calabi-Yau threefold, I can think about the Schön as being glued from 2 pieces. And now I can translate to the M theory using the replacement of the T3 by K3 by essentially replacing that bit with a open K3 fiber Calabi-Yau threefold times as 1, another 1, and a specific gluing between them. And once you have established this relationship, of course, you can now work out the spectra of light fields on both sides, and you can match them. And actually, we managed to write down a general proof that works. One comment is that on the heterotic side, of course, you start out with the 8 times the 8 gauge symmetry, and depending on how your bundle is chosen, didn't explain how the bundle data enters in detail, but depending how the bundle is chosen, you will have some non-trivial gauge symmetry. And if you do have some non-abelian gauge symmetry, then you can show that the corresponding G2 manifold should be singular. This is not something where the theorems that these people here have proven about existence of G2 metrics on that thing hold, strictly speaking. But if you speak to these people, then they will tell you, yeah. In the situation where you have these singularities, that will still go through, just nobody has proved it yet. At least that's what they told me. So that looks pretty good. So maybe I can ask a question at this point. How much time do I have left?
Oh, should be like 5 minutes, more or less.
Okay, very good, very good. I think I could speak for much longer, but I'm not going to do. Okay, very, very good. Thank you. So, okay, so this was essentially one instance where these G2 manifolds pop up in a string duality. There's something completely different that I want to talk about next, or that I want to at least mention, and that is mirror symmetry. So
can I have a question now?
Please.
So in this TCS G2 manifold, the heterotic dual must be this Schön Calabi-Yau.
That's right.
Okay, thanks.
So right, thank you for reminding me about that. Maybe it's something I should say. So I started now from one specific Calabi-Yau threefold, this Schön Calabi-Yau threefold, and I made a TCS G2 manifold. But there's not just one, there's millions. And of course, the choice I have in making different TCS G2 manifolds corresponds to different kind of topological configurations of gauge bundles on the heterotic side. Yeah? And of course, we know there's millions of Calabi-Yau manifolds. So we've now constructed millions of G2 manifolds that are M-theory duals of just one Calabi-Yau threefold on the heterotic side. That's quite an interesting thing to digest a little bit. Okay, so remember when I was speaking about T-duality and mirror symmetry earlier on, I was saying, the first one way of thinking about mirror symmetry for Calabi-Yau is you look at the massless fields of the effective supergravity, or you look at the world sheet, and the same stuff you can do for type 2 strings on G2 manifolds if you want. And if you do that, then what you learn is that there is a chance, let me say it like that the effective theory or the world sheet theory even is the same if the sum of the second and the third Betti numbers agree. It's a little bit less constraining than swapping H11 and H21, but then again, we have less supersymmetry. So, okay, maybe that's how it is. So this idea, again, has been around for a while. People made some, so there's a paper by Bobby Achaya on this, and there's a nice paper by Gabriel and Caste on this from 04, where they explain the role of this retorsion in those things, where people do this for orbifolds. And something that I did with Michele is that we understood that you can somehow identify torus vibrations also on these glued G2 manifolds, and then you can use that to somehow motivate a mirror map in the same sense of Strominger-Yau-Saslow. By the way, the story about the BPS states and the motivation I gave for the existence of these vibrations for Calabi-Yaus from BPS states is something that goes through in a variant also for G2 manifolds. So the basic idea is here that we glue two Calabi-Yau threefolds, open ones times S1 in this way. And of course, these open Calabi-Yau threefolds again have SYZ vibrations, and we can use them. And if you look at the way it's glued, you also have to take the fourth S1, and that gives you a T4. So that means if you construct the G2 manifold from the data, one Calabi-Yau threefold, another one, and this hyperkähler rotation, then this somehow motivates that you should make a mirror by changing the Calabi-Yaus to their mirror, and then you can also prove that there's sort of a mirror gluing in that case. And the cool thing is, once you have done that, there's a very nice way of constructing these things, and then you can again prove in general, and we did that in our papers, that this kind of relationship, that B2 plus B3 of these things is the same, holds. Funny enough, there's also a T3 fiber you can identify here, and that gives you a second mirror map, where you essentially only swap one of them to the mirror, but you leave the other one alone. And we also studied that. And in both cases, you can prove in general that this requirement is true. So in some sense, this vibration structure is, of course, something that's slightly subtle. And you might say, maybe that's a bit fishy, the way you talk about it. But that's not really relevant. I mean, the relevant point is that if you just look at these constructions that are well-defined, you can prove this relationship. And then you can somehow motivate that these things should be mirror by looking at these vibrations. Maybe let me skip that and let me make one final point, or let me explain one final application of this stuff that is quite cool, which is that if you have I spoke earlier about the fact that M theory on an S1 gives you type 2A theory. So now you can ask again, is there a fibered version of that that has something to do with 4D n = 1 theories? In other words, is there a fibered version of that that has something to do with G2 manifolds? And of course, if somebody shows you this kind of picture and says we put M theory on it, you might say, hey, maybe there's an M theory circle somewhere there where I can somehow relate this to type 2A on a Calabi-Yau threefold, or rather on Orientifold. And turns out that is true. So here's the story in a nutshell. So already a long time ago, Cutrer and McGreevy said that if you have a Calabi-Yau threefold and you do an Orientifold with it, so there's an anti-holomorphic involution you mod out, at least on the level of geometry, you can get a type 2A Orientifold with O6 planes and T6 branes. And that should be lifted to N theory on a G2 manifold that is a resolution of X times an S1 mod the Z2 acting on X and an inversion on the S1. Now, if the anti-holomorphic involution Z2 omega acting on X acts in such a way that it respects a K3 vibration on X, so it acts somehow purely on the base and on the fiber in the same time, but it doesn't swap stuff between base and fiber, then you can somehow think about decomposing this space M in the same way that we have considered before. And that's something I showed in a paper that was published recently. So what you do is you look at the base. If you have an anti-holomorphic involution on P1, then you essentially swap the two hemispheres and the equator is fixed. And so you can look at a fundamental region, which is just half of it. And you can somehow separate the region close to this locus from the rest and cut. And then essentially what you get is a picture like here. So the left-hand side is just S sitting over this somehow part of the upper hemisphere. And of course, in that region, there is no non-trivial action of this Z2. I mean, it acts at the same time up here and down here at this. So this is just S fibered over a cigar times an S1, where this S1 is the if you like, the M theory S1. Whereas if I look at the region close to this fixed locus, then the involution acting actually in the region on the base P1 orthogonal to this equator is trivial, and I can just factor that out, which is this as one. And the M theory circle now is, of course, acted upon non-trivially, so I can somehow combine it geometrically with the direction that goes around this. That goes in this direction. Sorry, what am I talking about? That goes, this S1 here is the direction that is parallel to this S1. I was talking too fast and confusing myself. This S1 is the direction parallel to that. And that's, of course, where the action is trivial because I swap northern and southern hemisphere. So anyway, when the dust settles, this kind of cutting gives you the same thing we had before, where the left-hand side is essentially just almost half of this Calabi-Yau threefold, and the right-hand side describes the region close to the fixed locus of this involution. And now the cool thing about that is that essentially that part where we don't see the fixed locus has to do with the closed string spectrum of the type 2A string, whereas the fixed locus of this involution, and in particular the smoothings of it, have to do with the description of O6 planes and D6 branes. And that is the open string sector. So you can think about this TCS decomposition of a G2 manifold as a decomposition that separates open and closed string sectors for type 2A orientifolds on K3 fibered Calabi-Yau threefolds with compatible involutions. All right, so let me stop here. I just have two summary slides. So to summarize all the stuff we've been speaking about. So I spoke a lot about M theory on two manifolds and a little bit how that has to do with type 2A orientifolds and what that has to do with heterotic strings and how you can use vibrations to cook up examples of such dualities. And of course, I would think about this kind of vibration story as more of a motivating thing than proving a duality. No, the real work that somehow is motivated by this is to now go and analyze these examples in much that we have cooked up in much more detail. So you want to know about effective actions. You want to know about all kinds of quantum corrections that you might have to the naive effective actions. And of course, you might also ask after that, how can we generalize this? Are there other situations that are at least easy enough where we have a handle to construct such things? And similarly for this mirror story, so we have now lots of examples where, oops, what happened now? Oh, my presentation ended itself. Very interesting. So we now have, sorry about that. So we now have lots of examples where where some of the first order check is satisfied, and one can claim that we expect there to be mirror instances of G2 manifolds. But the story is a little bit more complicated than for Calabi-Yau manifolds in that there are a bunch of mirror maps, namely ones where you use a T4, so you get type 2A goes to type 2A and B to B, and instances where you have a T3, so to A and B are swapped. And somehow one of the next things I started working on this is to really understand better from the worldsheet point of view what's going on there, because that is of course necessary if you actually want to prove that such a mirror map holds. And finally, you would of course hope that you can use such a notion to give from the physics point of view some well-defined counting problems similarly to what you have done for Calabi-Yau threefold. So you want to understand, are there interesting things you can count on these geometries related to corrections of the physics. Okay, I'm really sorry for going over time. Hope it wasn't too bad, but I wanted to at least flash a few things at you in the end. So thank you very much for your attention.
Yeah, well, thank you, Andreas, for the talk. Are there questions over there? So, well, I've got a question. So last part you were talking about how you can get, well, these six brains, well, some open string sector description with these twisted connective sums. How about getting, well, codimension 7, well, point like singularities, so chiral matter?
That's a good point, precisely. Thank you very much. That's a good question. Because, you know, I mean, some of the type 2A picture of this would be, oh, codimension 7 in G2 corresponds to point-like intersections between these six brains.
Mm-hmm.
That gives you chiral matter, precisely. So the point is, so there are okay. Let me say as follows. So first of all, if you look at these TCS manifolds, then you would say, of course I can make singularities. I can have singularities where every K3 fiber is singular. That gives me codimension 4 gauge groups. Then I can have situations where the K3 fibration degenerates further over some points here. Okay. That's really like matter in 6DF theory convectifications. Same thing. But of course, now these degenerations happen over points here, so they happen over the whole of this as one. So they're codimension 6. So they should give you non-chiral matter. Yeah. And now, of course, as a caveat, this picture, you shouldn't really, I mean, the Ritchie-Flat G2 metric on these TCS G2 manifolds is only approximated by the Ritchie-Flat Calabi-Yau metrics because of the gluing. There's a theorem that says that these exist and that they are close in a certain sense, but they're not the same. So then you might say, aha, so that means you can't just tell me that the K3 degenerates over a point, and that means you have codimension 6. So I wrote a paper with Sakura and some of her students where we looked at that from the somewhat effective gauge theory, twisted 7D gauge theory point of view. And there's also other ways in which you can argue that actually these codimension 6 singularities in the actual G2 metric will split up into codimension 7 singularities. But they do so pairwise. And you always get chirality plus and chirality minus together. Yeah, so somehow somehow you can use this to argue that on a TCS G2 manifold, there will never be a chiral spectrum for M theory. And that's very unfortunate. The same is true, by the way, for the heterotic string on this Schön Calabi-Yau threefold. You can also argue there that you will never get chirality. And now for the type 2A picture.
This is a consequence of the construction by the TCS?
Yeah, the construction is just, I mean, the construction is simple enough to allow you to pull this off, but then again, it's unfortunately too simple to give you something interesting. And it's not difficult to understand. I mean, somehow, if you think about, let me think about a K3 surface as, sorry, a G2 manifold as being K3 fibered in general. I have a K3 fibered over some 3 sphere, say. To get a point-like singularity, there has to be a special point on the 3 sphere where something happens. So the K3 moduli space, as I said, is a 3-plane in a 2-dimensional space. So somehow all 3 legs have to do something. The 3 legs are the holomorphic 2 form and the Kähler form. Right? So all 3 of them have to vanish, say, integrated over a cycle somewhere to get a codimension 7 singularity. Now that's the picture. And there are various instances where you can make this more precise. But now the trick in the CCS construction is to do some holomorphic stuff on one side and some holomorphic stuff on the other side, and then glue that in a way that destroys the holomorphicity. But holomorphicity means that only 2 of the 3 legs do something non-trivial.
Yeah.
Only the holomorphic 2 form changes, and the Kähler form just sits there on each side. Which one is which depends on how you look at it. But anyway, only 2 out of 3 agents are active here, and that's why you don't get codimension 7. That's another way of saying the same thing. From the type 2A point of view, again, I mean, in my paper, I analyzed somehow the map in some detail. How do you map now this geometry of the C2 manifold to the locations of these 6 branes and those 6 planes? And it looks very much like the Sen limit of F theory, actually, which is probably not a surprise. But unfortunately, what you see is, and of course you can also discuss that, you can also discuss that without thinking about G2 geometry too much. If you have an anti-holomorphic involution that acts on a K3 fibration in the way that I have shown here, so in a way respecting it, then the D6 branes will either not intersect or they will intersect over curves, over real curves. So you don't never have these point-like intersections. So again, you don't get chirality, and you see that from the D6 brane picture as well. So that's unfortunate. I mean, that's so if you think in terms of phenomenological applications, that's very unfortunate. Yeah.
Andreas had a different kind of question about this mirror symmetry for G2 manifolds. So I seem to remember that in the Chatashvili-Vafa paper, they had some kind of understanding at the worldsheet level in terms of the twist of some universal tricritical Ising sector in the compactification.
That's right. That's
but
right.
Here you seem to be exhibiting two kind of mirror maps. So have you been able to identify two different twists, one which is relevant to A and to B?
That's a very good question. So it's a little bit more, I mean, so Chatashvili and Vafa also say another thing, by the way. I mean, first of all, they identify this twist. So in some sense, there's no spectral flow, but there's like a discrete spectral map. I think that's the idea. But I think it's not clear if that is unique or if that can only be done in one way. And correspondingly, Chatashvili and Vafa make a very strong conjecture. They say, look, for the Calabi-Yau threefolds, we should swap H11 and H21. And then they say for G2 manifolds, we expect the thing to be much more soft in a way, where only B2 plus B3 have to be the same.
Well, that's a necessary condition, but of course, you really want the CFTs to be isomorphic, so it's a much longer.
No, of course, no. But what they conjecture is that actually the word mirror symmetry is a complete misnomer for G2 manifolds, and we should think that they don't come in pairs, but they come sort of in families. Well, not families. Family is the wrong word. They come like in sets. So there's not just two, but there might be 3, 5, 7. We don't know how many G2 manifolds that are all give you equivalent type 2 compactifications. So that is the picture that they motivate somehow. So that means that or from the point of view of the worldsheet, that means that there must be several inequivalent ways to do these twists.
And in your construction, have you been able to check the mirror symmetry just beyond the the B2 plus B3 being the same?
We have done that in one instance. So the one instance where people have really worked out what happens from the worldsheet level is the orbifolds. So in this nice paper by Gabardine and Custer, what they did there is they looked at some of these T7 mod gamma G2 orbifolds, these Joyce orbifolds, and you can of course now work out the spectrum of type 2 string theories on that orbifold. And what they do in this paper, I mean, the somewhat most difficult part is to work out what consistent assignments of discrete torsion phases you can have. And then you find in this instance, for example, that there are actually 9 different. I mean, the simplest choice is where this group gamma is Z2 cubed, yeah? And there's one specific instance of that where already Joyce figured out that there are 9 different resolutions of that.
Does it fall into the class of TCS manifold that you looked at?
Precisely. So that's the point. It does fall into the class of TCS manifolds we looked at. And in one of our papers, we wrote that down. We explained that in detail how that works. And then, of course, after we've done that, we can check, we can see these 9 different resolutions. Gabardine and Custer tell us which ones are mapped to which under the mirror map, because the mirror map does to the discrete torsion what it usually does. And then we can match that with our recipe for mirror maps. And it works.
Okay. Thank you.
It works. So in that instance, we would say that we have something on the worldsheet. But to be honest, I mean, one of the things I started working on that I'm of course interested in is trying to understand that from the worldsheet point of view in more general situations. So then you maybe want to look at some Gettner models in that instance. And there is a notion of that.
Right. Thank you.
Any further question? If not, I think we can thank Andreas again.
Thank you very much.
And well, let me stop recording. Oh, okay, that's it. Well, so yeah, thank you very much, Andreas, for the talk.
Thanks for the questions. You just
Thanks,
asked.
Andreas. Maybe I can ask some more question about this Schön Calabier.
Happily.
So you made a strong statement